Okay, so based on those limitations, primarily the issue of these separate outputs creating problems in terms of how to build up a knowledge base, really, because this is one of the most interesting things here is that the diagram before this one gives you the basis by which you can actually think about creating within, at least this is a network structure, a neural network structure, a collection of background knowledge, task knowledge over time that grows and grows and grows and is helpful to learning more of the same over time. So that it is a knowledge acquisition system to some extent. But there are these limitations. So that drove us to thinking about another way of doing this. And this was one of these things where, as the professor, I thought about this back when I was doing the very end of my PhD, but it was like 10 years later, and a master's student said, you know, why don't we just change the data, the multiple task data, such that instead of having multiple outputs, we only have one output. And what we do, alternatively, is we add on to the front of this a series of context nodes, you know, C1, C2, C3, C4, where if this node, if this input, if this input parameter is on and all the others are zeros, then this is an example for task 1. And if this one is on and all the others are zeros, then this is an example for task 2. And the beauty of doing this now is that we can use any standard learning system. The reason why I didn't do that back a long time ago was that for the people that have worked in this area, there's a thing called the curse of dimensionality. When you add more inputs to your problem, you increase the challenge of finding the appropriate model. So by adding more contextual inputs here along with the primary inputs. So again, if this is our problem of trying to diagnose disease, build a model for diagnosis of disease, this is your age and gender and medical clinical parameters, stuff like this. Now we're going to add a bunch of contextual inputs for different tasks in the domain. Just would seem to make it generally a worse problem. And it turns out that the student was right. It doesn't actually. Surprisingly, within this paradigm, if you do this, it works quite well. And transfer actually seems to work as well as the standard technique of having multiple outputs on this side. And seemingly, the issue of trying to choose the most related task goes away to some extent, too. So we developed this alternative approach called context-sensitive multiple task learning. It uses a single output neuron network structure. So now you're learning a function f of c, the context inputs, as well as the primary inputs. The inputs associate themselves with a particular task. Or, by the way, another way of thinking about this is that the context inputs could be grounded. They could actually be inputs from the environment, such as the XY coordinate for your robot, or the light level, or something like this. So those actually modulate, if you like, the input parameters as contextual cues. All the weights are shared now in this network. So you've got the learning is shifted now from learning separate task outputs to learning a domain of all the tasks. And our conjecture was that no measure of task relatedness was required. Well, I can't tell you that directly. We actually have seen variations in the accuracy of the models based upon which tasks are being learned, but the effect is not as dramatic under this paradigm as it was with the multiple outputs. So it eliminates redundant outputs for the same task. It's one of the nice things. You're not building additional outputs, and therefore the problem of practicing something under the multiple task learning paradigm before with multiple outputs was that you kept on adding a new output for every set of new training examples you might come across. And therefore you'd have multiple outputs for the same task. That doesn't, so there's a whole bunch of housekeeping stuff to take care of there. With this arrangement, you can have your examples in any order that you want, coming in and for tasks, and it will put them together appropriately. Now the inputs themselves tell you which task a particular example is for. So you don't have that problem of figuring out which examples for which tasks. And it does tend to develop this more fluid domain of tasks. When you're finished building the models, effectively, you can really think of these as being biases, just like that. When this particular context node is on, for the same set of input parameters, you're going to get a particular output here for that task. As you change this from a 1 to a 0, and this from a 0 to a 1, now what's happening is that you're moving in the hypothesis space, and you're actually indexing into it in different locations, and producing, selecting models for this particular task. And it's hard to analyze what's going on in these networks with the complexity of them, but there seems to be a much smoother flow.
Could you give us an example of the diagnostic task? What would be a context input versus a primary input?
Well, in its simplest form, the context inputs are just simply the examples for task A, task 1, or if it's for task 2, or task 3, or task 4. So if we're learning, for example, the model for diabetes, then we would have our context node 1, C1 on, and all the other ones are 0. And then we have our example inputs for that particular diabetic problem, and the output is simply 1 if the person has diabetes, or 0 if not. Now, if we have an example for heart disease, then C1 is a 0 and C2 is a 1, because that's the context input that says that this example is about heart disease.
So it's a classification.
Yeah, well, it associates the example with the particular task. That's the simplest way of doing it. If you want to ground it in something, you could say that C1 and C2 are the X and Y coordinates in this room for your robot, right? And maybe a third parameter, a contextual parameter, which is the relative light level. And those three things, X, Y, and light level, actually contextual cues for indexing over the hypothesis space for all of the other standard inputs. Really, this is just your traditional learning problem now, viewed in a slightly different way. It's no longer learning one task, it's actually learning multiple tasks, and the contextual information is providing the method of separating the examples from one task and another. So this is results of comparing this learning system against, in red, so yellow is the new, red is the older multiple task learning, and blue is if you use just examples for the primary task. So the way we usually set these things up is that, first of all, if you have lots of training examples for a particular problem at hand,